All right, so welcome back again for the third and final part of Quivers and Cohomological Hall algebras. Glad you are still here. So the rules for three-part mini course is, in the first part you should start really easily, which is easy because you have all the time in the world. 3 times 1.5 hours, wonderful. Then in the second part can be challenging and you can do the dirty work, which we did yesterday, yeah? All these actual calculations. I will briefly repeat this. And then in the third and final lecture, you have to round everything up and connect all the loose strands, discuss everything you promised to discuss, and that's quite challenging for me. So let's see how this will work out today. And have to admit, I forgot my section numbering. So did anyone take notes? And was section 5 the last one I gave you yesterday? 5 examples? Okay. Wow. Okay, so I remembered correctly. Okay, so yesterday we did the actual hard calculations. And so what we did yesterday was calculating in Cohas. And so just a very quick reminder. So the Coha was a structure building on the GD equivariant cohomology of RD. These were the representation spaces of Quivers with the gauge group action and with a strange multiplication coming from a correspondence motivated by exact sequences. And then we saw that this has the shuffle realization, that this is isomorphic to shuffle algebra with kernel. And this vaguely, roughly looked as follows. So it was isomorphic to a direct sum over all D of a ring of polynomials in variables x, I, k, I a vertex in the quiver, k running from I to di, symmetric with respect to each set of variables. And with the product, I will not repeat it in detail, but the product of f and g is defined as the sum over all I prime, I double prime, DE shuffles, f of xi prime, g of xi double prime, and then a shuffle kernel, which was essentially just a huge product over differences, x dot dot, x dot dot. I will not give the details again. Yeah, and then all the time we will see that these might give denominators, and we have to see why the denominators ultimately cancel. You can always write this in some normal ordering, introducing signs here, and we did all the calculations with symmetric polynomials. Yeah, and actually saw some examples. So what we discussed was the example of the trivial quiver, in which case the Coha was an infinitely generated exterior algebra. One loop quiver, in which case the Coha was an infinitely generated symmetric algebra. I briefly gave you a formula showing that the set of generators explodes for the two loop quiver. We'll see this phenomenon again. And we briefly discussed one non-symmetric case, the single arrow quiver. Yeah? So, okay, this is what we did yesterday in a very brief summary. Okay. Okay, so now I will tell you the general story starting from these examples, and this is the story for symmetric quivers. I will tell you in a second what a symmetric quiver is, and I will motivate the consideration of symmetric quivers from the very definition of the Coha. Yeah? So you can really see from the definition, yes, it's definitely a good idea to look at symmetric quivers. And then we will see how this leads us to motivic Donaldson-Thomas invariance, aka BPS state counts. So these motivic Donaldson-Thomas invariants of very general categories were introduced by Kontsevich and Seubermann 2 years before they defined the cohomological Hall algebra. And this was meant as a mathematical precision of BPS state counts. All right. So, and then we will see two theorems about that. No, 3 theorems actually. And then we will see that we have to come back to the geometry of quiver representations, somehow taking up one of the loose strands from the first talk. All right, so first of all, let me introduce one tool which I already wanted to introduce yesterday, but I just didn't need it, the so-called Euler form of the quiver. The Euler form of the quiver Q. This is a non-symmetric bilinear form on tuples of integers, zq0, zq0 to z, and it goes as follows. The Euler form of 2-dimensional vectors dE, well, you take the sum over all dIEI, coming from the vertex structure of the quiver, and then we have a contribution from the arrow structure of the quiver. Namely, we take dIEJ whenever we have an arrow alpha from I to j. This is in general non-symmetric bilinear form which pops up everywhere in quiver theory. Yeah? It has a meaning in terms of the representation theory of quivers. It's the so-called homological Euler form of the category of representations. It pops up in considerations of the geometry of quiver representation, which I will show you in a second. It pops up actually in the definition of the Coha, because if you remember this shuffle description, there was a certain exponent for the shuffle kernel, which was number of arrows from I to j minus Kronecker delta ij. And we can now actually rewrite this, this thing as minus Euler form ij, where I and j mean the coordinate vectors. Yeah, so implicitly was already there. We have already seen it in the Coha. So just as an example where this plays a role, we have seen the group and the space GD and RD. Yeah? RD was this universal parameter space for quiver representations. GD was the gauge group, and that was the action which we used for the definition of the Coha. And if you just take the complex dimensions of this affine space and of this variety, you will see that this is nothing else than the quadratic form associated to the Euler form. It's just DD. DD. Yeah? So that's, for example, where this naturally pops up in the geometry of quiver representations. All right. So we call the quiver Q symmetric if its associated Euler form is symmetric. Yeah, and we will see why we really want this to happen for some things. And in other words, this means for every pair of vertices, the number of arrows from I to j is the same as the number of arrows from j to I. Equivalently, for all I and j, the number of arrows from I to j equals the number of arrows from j to I. All right. Okay, so that's now the important terminology for this section, symmetric quivers. And now we'll see why symmetry of the quiver matters, namely in the very definition of the cohomological Hall algebra, in the definition of the cohomological Hall algebra, there is a shift in cohomological degree, which I haven't told you about yet. There's a shift in cohomological degree. this is something I promised to explain, and now I have to do it. And then you will see immediately why symmetry of the quiver matters. Namely, so we have defined this star product on equivariant cohomology. And the star product in equivariant cohomology, I will not write it down again, but I will just say from where to where does this map go. We remember this was a map from GD equivariant cohomology of RD cross GE equivariant cohomology of RE to GD plus E equivariant cohomology of RD plus E, because the Cohen multiplication was always graded with respect to the dimension vector. But I just wrote down dot, dot, dot here for the cohomological degree. But now, if you go carefully through all our steps in actually defining this product using general features of equivariant cohomology, you will see that the following happens. If you start in cohomological degree k, respectively L, then you end up in degree k plus L minus twice the Euler form of D and E. K plus L minus twice the Euler form. Aha. So that's where the Euler form really matters. And this gives us an opportunity to modify the grading so that the Coha is really, this means that the Coha it's graded with respect to the dimension vector. It's definitely not graded with respect to cohomological degree because you have the shift. The question is, can we modify the cohomological degree such that the algebra is graded? And this is now the key observation again. All right. Small observation. If Q is symmetric, then Coha of Q is not only graded by dimension vector nq0, but also by cohomological degree if you define, now comes the central definition, if you define Coha of Q in degree dk as the GD equivariant cohomology of RD, but now you take k minus Euler form dd. Yeah? So we define a new grading on the cohomological Hall algebra by shifting the cohomological grading by this quadratic form. Yeah? And then if you try to work out that this is indeed graded with respect to this degree, using this formula, then you see the only way you can do this is if Q is symmetric, if DE actually equals ED. Because what you do is you rewrite this twice DE as DE plus ED, and then everything works fine. It's really just a one-line calculation. It's a small observation, but absolutely central to the theory of cohas. So that's the observation which you can easily make. And based on this observation, Kontsevich and Seubermann conjectured that the Coha with respect to this grading has good structural properties, whatever that means, in this case, in the case where the quiver is symmetric. And this conjecture was very quickly confirmed by Efimov. And now I'll write down Efimov's theorem in full generality. If Q is symmetric, then the cohomological Hall algebra of Q with respect to this grading is automatically a graded symmetric algebra over a certain set of of a certain space of primitive elements, and then you have a free variable z in degree 0, 2. Yeah, okay. So this is the big theorem, one of the first big theorems about cohas. Now will explain all this. So this means graded symmetric algebra means either symmetric algebra or exterior algebra, depending on whether you are in even or odd degree. Yeah. So this is a symmetric or exterior algebra, depending whether you are in even or odd cohomological degree. I mean, even if this equivariant cohomology a priori only lives in even degree, because we are shifting everything by this Euler form, it might happen again that we have even and odd degrees. Yeah, and depending on that, actually, there's one tiny little detail which I don't want to tell you. This grading is a bit more complicated, yeah? So this, whether it's symmetric or exterior, you have to put in a tiny little extra sign, but please let me ignore this, because it would require several blackboards of explanation for nothing we will ever see in an example. Yeah, okay. But this is explained in the literature, and I forgot to give you one link. Okay, this I will do in a minute. Okay, so this is a symmetric or exterior algebra, and you always have somehow a free generator in degree 0, 2. Degree 0 with respect to dimension vector, degree 2 with respect to this twisted cohomological grading, and these vprin, about this we know that it is finite dimensional in every single dimension vector. Yeah, so even if we sum up over all twisted cohomological degrees and just fix the dimension vector, it is finite dimensional. And I've shown you one formula for this actual dimension yesterday. For the 2-loop quiver, this was this complicated Möbius inversion formula with the binomial coefficients. All right, so that's Efimov's theorem. And Efimov's proof, which was actually the content of his master's thesis, was by brute force. He just took this shuffle algebra description and did a Gröbner basis argument. Yeah? He just said, well, okay, if I have enough generators for the symmetric algebra, then I'm done. If not, I'm taking a complement, and I have a certain normal ordering on the basis elements, and then he does a Gröbner basis argument. And so by brute force commutative algebra, he manages to prove this theorem, which is really astonishing. And by now, there are around 10 different structural interpretations for these spaces vprint. So let me just say it has several structural interpretations. I once did a list of all of them for an overview talk, and I think it was 9 or 10 different interpretations are now known. Among them, there are combinatorial descriptions. There are algebraic descriptions, for example, in terms of vertex operator algebras and in terms of Lie superalgebras. So in terms of vertex operator algebras, in terms of Lie superalgebras, and in terms of certain cohomology theories of moduli spaces. And today I will give you this moduli space interpretation. And I cannot tell you anything about these algebraic interpretations at the moment. I will give you the moduli space interpretation. This is maybe what you really want to know, because if, starting from this lecture series, you want to look up not the quiver case, but for example, the 3 Calabi-Yau case, quivers with potentials or whatever, And you want a similar structural theorem for the Coha. Yes, it exists. And this is the thing which generalizes to say, the three Calabi-Yau settings. I will indicate this in a minute. Yeah, so this is the structural interpretation which we will use. But Efimov's proof was just brute force, just this primitive space exists. Yes, you always need a certain symmetry for some associated homological Euler form, definitely. So in the non-symmetric case, this is nothing you can ever expect. Yeah. All right, okay. Yeah. yeah. Well, I mean, so we have seen this cohomological, the Coha product, yeah? And at the end of my first lecture, some of you ask about, is this map surjective? Well, in general, it's not. So how do you find this set of generators V print? Well, you take the smallest degree D and E, and you take everything there, and then you calculate the image. And then the image is not everything, and so you take a complement to the image, and you take this as new generator, and you continue inductively. And at the end, you've built up a space V print, which you have no idea about. It's just there. It's just orthogonal complements to the image of the multiplication map. Yeah. And then the hard part of the proof is to show that the only relations you have to these generators are that commutators or anti-commutators are zero, and there are no more relations. And this is the Gröbner basis argument, where you really order all the bases of the print you found, you write down ordered monomials, and then that's the hard part of the proof. Yeah. Exactly. Yeah. So this was precisely, I mean, this V-print just measures how non-surjective the multiplication map is, roughly. Yeah. So that's answering your question from the end of the first talk. Aha. So one loose strand connected. All right. I will show you in a minute this moduli space interpretation, but before that, I will show you Donaldson-Thomas invariance. Now, associated to any graded algebra, you have a partition function, a formal series encoding all the dimensions of the homogeneous parts. Or in commutative algebra, you would call it the Poincaré-Hilbert series. And let's look at the partition function encoding the dimensions of the homogeneous parts here. So what does Efimov's theorem tell us about the following partition function ZQQX? That is usually called the motivic generating function of the quiver. And this is defined as, I take the sum over all D in NQ0, and I take the sum over all integers K, and then I take the dimension of Coha Q dk, this part, the new grading. Then I take minus q to, for certain reasons, minus q to 1/2 to k, and then x to d. This is a formal power series in lots of variables. This x to the d means you have one variable xi for each vertex in the quiver, and you take this variable xi to the power di. Yeah? That's shorthand notation just for monomials in a polynomial ring. That's an extra variable, and for certain reason, it's a good idea to take not q, but q to 1/2 as the variable. The motivation for this comes deep from this motivic stuff, which I will not talk about. So this is a partition function which you can naturally associate to a quiver. It's just shows you the size of the coha. Yeah? And what does Efimov's theorem tell us? Well, first of all, this is easy to calculate from the definition. From the definition, you can calculate this as a so-called Q hypergeometric series. So you can really express it in elementary terms. This looks as follows. You take the sum over all D, dimension type. Then you take minus Q to 1/2 to the power dd. Again, this quadratic form associated to the quiver. It's now everywhere. The denominator is a standard product of so-called Pochhammer symbols. I'll write it down. 1 minus Q inverse times 1 minus Q to the minus I. And then finally, x to the d. This looks like magic that you can actually compute this series. I will now tell you why this is actually easy. So why can we calculate this partition function of the coha just from the definition as something which is totally explicit? This is a totally explicit series. The only ingredient it needs is a certain quadratic form, the quadratic form associated with quiver. Why can we compute it? Well, this dimension part of the coha is the equivariant cohomology of Rd with respect to the group Gd. And we have seen yesterday, in deriving this shuffle description of the coha, that this is the same as Gd equivariant cohomology of a point. Yeah? That was the first step in computing this, in describing this shuffle product. The same as the point. And that was this algebra of symmetric polynomials. And now yesterday I've told you this fundamental theorem of symmetric polynomials. Every symmetric polynomial is a polynomial itself in so-called elementary symmetric functions. And if you apply this main theorem of symmetric polynomials and work out what it means for the partition function, you directly arrive here. Yeah? So it's fair to say from the definitions, what you only need is the fundamental theorem on symmetric polynomials. Okay, this is a Q hypergeometric series. And now Efimov tells us that this partition function is the same as the partition function for this graded symmetric algebra. And partition function of graded symmetric algebras, it's also not too difficult to see, are products. Products, infinite products, where the exponents are the dimension of these primitive parts. Now the details are not very nice, but I have to write it down once. Efimov tells us that the motivic generating function of the quiver has an infinite product factorization over all D, a product over all non-negative K, a product over all integer I, 1 minus Q to the K plus I plus 1/2 x to the D, to the power minus 1 to the I plus 1, and then the dimension of the primitive part, dim V prin di. Okay. Now say, okay, yeah, maybe cool formula, but so what? The answer to so what is that in the earlier paper of Quivers and Solbermann, where they defined the motivic dt invariance as a precision of BPS states counts, they defined dt invariance as follows. Take a partition function, write down an infinite product factorization, and look at the exponents. These are dt invariants. So these are precisely the exponents. Yeah? So motivic dt invariants in the sense of Quivers and Solbermann are precisely dtd associated to the quiver Q. This is the sum over all I. We'll have to be careful about one shift. Minus, of course. No, It's the dimension of this V prin di minus q to the 1/2 to the power I. So, and this is precisely the definition which Kontsevich and Säubermann gave of these motivic TT invariants. Yes, please. Now, I was just trying to be suggestive. I mean, this somehow feels like a partition function of something. No, it's, I mean, you're just writing down a generating series of counting states. Yeah. Okay, so D is the energy level, and these are states at energy level D. And we are enumerating them by taking the dimension of the space. No, this was, I was just trying to be suggestive.
So there can be other functions that can be equivalent for the partition function.
Yes, yeah. So what I, okay. Okay, so I mean, I wrote down what I had to write down, because that's the key mathematics behind this theorem of Efimov. And now, okay, so what, maybe you don't want to see the details, but what can you learn from this? What you can learn from this is, whenever you have a formal power series, which you might call partition function, yeah? I mean, you're enumerating states of some theory at arbitrary energy level or charge level or whatever. Take this series. If it's a power series starting with constant term 1, then you can write it as an infinite product. That's always possible. Yeah? Write it as such an infinite product of monomials, 1 minus a monomial, and then there are some exponents popping up. And the general principle is, these exponents are automatically interesting. They might have a deep meaning for your theory. Yeah? That's the idea. And why is this true, that they might have a deep meaning? Well, look at this example here. And let's work in the other direction. You can say, well, we just took a series which is maybe not the first thing you think about, but just a nice Q hypergeometric series which you can associate to a quadratic form. And we just do this principle, well, you have a series, I just write down this Euler product factorization, like this. And what are the exponents popping up? And now we see that this has an algebra upgrade to saying that the Coha, which is a very, very complicated algebra a priori, actually is something very simple. It's nothing else than a graded symmetric algebra. So just commutator or anti-commutator 0, no more relations, over some space of generators. And the space of generators we don't know, but that's the exponents popping up there.
So is this factorization a result that we always have this Efimov kind of equivalence for the left-hand side? Or?
Yes, yeah. I mean, whenever, so you have such a nice product factorization of your partition function whenever your partition function is the generating series for an algebra, which has such a nice structure. Yeah. Basically, we will see this again at the end of the talk. Okay. Oh, yeah, so that was a bit hard, yeah, because, well, I mean, both this sum here, this hypergeometric function, and this triple product over strange terms, it's not something you might like immediately, but in motivic Donaldson-Thomas theory, that was a big step, because what it proves is that these motivic DT invariants have non-negative coefficients, yeah? The coefficients are actual dimensions of vector spaces, and that is not clear a priori. And in particular, if you do all this with a non-symmetric quiver, it all fails. You might take a non-symmetric quiver, write down this series, and brute force factor it into an infinite product. And the exponents popping up are a mess. Yeah? So they're definitely not non-negative. All right. Yeah, okay, so that was a brief excursion into motivic DT theory, because that's somehow naturally connected to all this. Now, let's take 2 steps back. And I will now give you this structural interpretation of reprint in terms of moduli spaces in the simplest possible case. And now formulas will be very clean again. So I promise not to come back to these DT invariants. All right. Part 7 of my series. Geometry of Quivers representations, part 2. Okay, and that's now really taking 2 steps or even 3 steps back. Forget about all this Coha and DT stuff, and just go back to this small section, Geometry of Quivers representations, part 1. What did we do there? Well, I mean, I introduced on Monday this classification problem of representations of Quivers up to equivalence, and we saw that we can reformulate it as saying we have this gauge group GD acting on the parameter space RD, and the equivalence classes are the orbits. So we already saw from part 1 of this that the action of the gauge group on the parameter space in general has bad orbit structure, whatever this means. In particular, in general, if you just take the orbit space, RD by GD, with its natural topology, this has a very bad topology. It's non-Hausdorff, you have non-closed points, etc. It's bad topology, non-Hausdorff. So you cannot separate points. You have non-closed points even. So these are not the spaces you want to do topology or even, I don't know, analysis or differential geometry on. Yeah? You don't want to deal with non-closed points or points which you cannot separate. And we have seen a little bit where this problem comes from. Namely, you have orbits of different sizes, yeah? And you have very small closed orbits, and you have larger orbits which have the smaller orbits in their closure. And now from this comes a very simple idea. What if I just take the closed orbits and just try to find an orbit space for the closed orbits? Because apparently the problem comes from non-closed orbits. And already in a very early 20th century, Hilbert told us, yes, that's exactly the right idea. The closed orbits, the space of closed orbits has a nice structure of an algebraic variety again. And this I will now define, and we will see examples. So theorem, and this is essentially really Hilbert from 1900. If I take RD, do I need a notation for this? No, okay. The set of closed orbits of GD in RD admits the structure. So if I write it down like that, it's just a set. Yeah? You would call it moduli space, but at the moment it's not even a space. But it admits the structure of an affine algebraic variety. Affine complex algebraic variety. We don't need the definition of a variety. It just means you can put on this a structure so that it is the set of solutions of polynomial equations in some complex vector space. Yeah? So This means can be defined by polynomial equations in some complex vector space. And it's not the end of the theorem. It's one more thing. And then we can look at two very nice examples. Yeah, so we're taking the set of all closed orbits. And then we get rid of this problem that we have non-closed points in the orbit space, naturally. No? Because all the potential closure relations are gone. But actually, this has a very, very good structure. You can identify this with a set of solutions to polynomial equations in a complex vector space. This is one of the best spaces you can define. Yeah? And I can even tell you, I cannot tell you the polynomial equations, but I can tell you which complex vector space you take. You need coordinates. Coordinates are given by traces along oriented cycles. Traces along oriented cycles. This is a bit mysterious, but that's the slogan you have to remember, and then you can work this out in any example. And if I formulate it like this, it's not only the theorem of Hilbert from 1900, but that's also a theorem of Le Brun and Procesi from the late 1970s. Okay, and so we will now work out this slogan in two particular cases, and then you will see what moduli space we take. So the resulting space we call a moduli space. MD of Q, and here the exponent is semi-simple. I will not explain this. It just means we're parameterizing the closed orbit, but that's somehow the official name for this moduli space. And there will be another moduli space at the end of my lecture, and that's why I need this notation. Do I really need it? No, I keep it like that. Okay, so that's again lots of information, and let's just work it out in an example, or in two examples. Yes. Okay, so let's take the following quiver, which not too accidentally is a symmetric one. So the quiver has two vertices, I and j, and arrows alpha, beta from left to right, and arrows gamma, delta from right to left. Let's write down the action for, okay, let's take the dimension vector to be, let's start simple. Let's take 1, 1. So we do not really deal with matrices. We're just dealing with scalars, but it's interesting enough. And now I will write down the action, GD on RD is given by the following formula. The group GD is given by a copy of GL1 at each vertex. GL1 is just a non-zero scalar, so we are given two non-zero scalars S and T, and with them we act on the representation space. And the representation space is, well, represent each arrow by a 1-by-1 matrix, A, B, C, D. Okay? And what is the formula for this? If you look up this formula, then this is given by T by S times A, T by S times B, S by T times C, and S by T times D. Now try to imagine how the orbits for this action look like. It's a bit difficult because, well, four-dimensional space. The orbits are basically something like, they somehow feel like hyperbolas because, well, you are scaling A and B with the same factor T by S, but you are scaling C and D with the opposite factor S by T. Yeah? And for example, a hyperbola xy equals 1, that arises if you take the point 1, 1, and you scale the first coordinate by a factor and the other coordinate by the inverse of that factor. Yeah? So it looks like the orbits might be generalized hyperbola. And now we'll compute the moduli space by taking this, this principle here. So the moduli space, which I defined here, has as coordinates traces along oriented cycles. Traces means trace of a matrix. Well, luckily for us, there are only 1 by 1 matrices here, so we don't have to take traces, but we have oriented cycles. Namely, you see 4 basic oriented cycles. I can go with the arrow alpha or beta from here to here, and then with gamma or delta, I can go back. So it actually turns out these are enough. So this has as coordinates A times C, A times D, B times C, B times D. These are 4 coordinates. And you can see, if you work this out, these 4 coordinates, if you know these 4 coordinates, you know the closed orbits. This separates all the orbits. And if we call these coordinates x1, x2, x3, x4, then we see one polynomial equation satisfied by them. So satisfying x1, x4 equals x2, x3. So this is the conifold singularity. Aha. So our moduli space is the conifold. So that's how it works in general. Of course, in general, the calculation will be much more sophisticated. But in general, if you have such a quiver setting QD, you write down the action, you are looking for this moduli space. You're looking for coordinates by taking traces along oriented cycles. And you need to take as many traces as you need to separate all the orbits. Yeah? So your coordinates have to know the closed orbits. And then you're looking for polynomial equations satisfied by these. And you come up with a list of polynomial equations. This can be very complicated. So for example, the worst case, which I think was ever computed, was triples of 3 by 3 matrices, where you need minimally 48 generators, 48 coordinates, 48 traces along cycles, and 365 polynomial equations to define it. And this is minimal. Yeah? So, I mean, this is a very nice theorem. It has its limitations. In general, you cannot really work this out. But let me show you one more case, which is a very, very nice exercise, which one should definitely do when one wants to compute, describe moduli spaces of quiver representations. So the other example is, the quiver is a single vertex and 2 loops. This is the one which is already as bad as possible, and the dimension is 2. So a representation looks like pairs of 2 by 2 matrices. Yeah? And it's very interesting to see that this moduli space is isomorphic to a 5-dimensional space with coordinates, the following 5 traces along cycles: trace A squared, trace B squared, and trace A times B. So in this case, X is not short for example, but for exercise. So I can really recommend this. So this means, well, if you know trace A and trace A squared, you know the eigenvalues of A. If you know trace B and trace B squared, you know the eigenvalues of B. Yeah? So if you only consider A and B independently, then knowing the eigenvalues, you know everything about closed orbits. But now you are scaling A and B simultaneously, so you need a mixed invariant, which is trace AB. And then you can see that if you know about these pair of 2 by 2 matrices, these 5 numbers, then you know the whole closed orbit. So this already separates closed orbits, and you can choose them freely. So they're completely independent, no polynomial equation at all. That's a very special case, and that's very instructive. So this is a second example of moduli spaces. So this is moduli spaces without any stability. Yeah? We are not yet at the point where we need a stability. This will come in 10 minutes. This is the moduli space just parameterizing closed orbits. Now, this is precisely what we need for Efimov's theorem, as we will see in a second, but let me warn you that this is only interesting for symmetric quivers. Because in a symmetric quiver, if you have as many arrows from I to j as you have from j to I, you have lots and lots of oriented cycles. But imagine your quiver has no oriented cycles, then what does this theorem give you? Well, the coordinates are traces along oriented cycles. So if there are no oriented cycles, there are no traces, and there are no coordinates for the moduli space. How come? Well, the solution is that if your quiver has no oriented cycles, then in each dimension you have only one closed orbit. So all the moduli spaces are single points. So final example. If Q is acyclic, so no oriented cycles, then GD on RD always has a single closed orbit, namely 0. That's it. And all other orbits have 0 in their closure. Yeah? So, and then all these moduli spaces are just single points. Yeah? And this means that with this approach to moduli spaces, we are losing tons of interesting examples. This we will remedy in 10 minutes using stability. But at the moment, let's just live with this. This is a concept of moduli space, which is there, which is interesting only for curves with lots and lots of oriented cycles. And the moduli spaces we get are given by polynomial equations in affine spaces. So they are absolutely non-compact. Yeah? Polynomial equations in an affine space. So they're never compact. They're only compact if they are a single point. So you get non-compact moduli spaces. And also, these moduli spaces are definitely not manifolds. Yeah? As we have seen in this example, you produce, even in a very simple example, you produce a conifold singularity, which is a quite severe singularity. Yeah? So your spaces are not manifolds and not compact. Very far from that. Yes, please.
So you said we use Efimov's theorem, but I thought Efimov's theorem also applied to non-closed orbits?
No. You will see this Efimov's theorem is that there exists this space V'. And now I will show you the next theorem, which gives a geometric interpretation of this V'. And it is in terms of this moduli spaces, so Efimov doesn't see the non-closed orbits. Yeah. Which is absolutely no limitation. In the symmetric case, everything's fine. Yeah. Okay. So that was the quickest introduction to moduli spaces of Quivers representations I ever tried to give. It was definitely very hard crash course. I mean, usually I give a lecture series of 3 or 4 lectures just on defining these moduli spaces and working out examples. Sorry for that. Okay, but at least now finally I can formulate a theorem. This theorem is based on Efimov's theorem. We cannot prove it independently. So this is the theorem which was originally proved by Sven Meinhardt and myself, and then a much, much better and general version due to Davison and Meinhardt. And this version by Davison and Meinhardt is the one which generalizes away from Quivers to Quivers with potential to 3 Calabi-Yau categories to anything you can ever imagine. If Q is symmetric, then the space V prim of Efimov's theorem, the space of generators, or the space of BPS states, is isomorphic to cohomology of the moduli space. But now we just have to be very careful about cohomology. So we take this moduli space, MD semi-simple of Q, and we take, well, I would like to write down cohomology of this. This just doesn't work. Because cohomology, singular cohomology, is a very nice cohomology theory for compact manifolds. For compact manifold, it has many, many beautiful properties. Poincare duality, finite dimensionality, whatever. This is completely the opposite. This is absolutely non-compact, and it's highly singular. So you better don't take usual cohomology. What you take is so-called intersection cohomology with compact support. That is another cohomology theory, IH dot index C. So let me write down what this means. This is compactly supported intersection cohomology. So intersection cohomology was invented in around 1980 by Goreski and McPherson, precisely as a cohomology theory which is still good for singular spaces. And they managed to set up a cohomology theory which is great for singular compact spaces. The C means compactly supported. That is just because the space is non-compact, but that's not the problem. Yeah? So intersection cohomology is a great cohomology theory for singular spaces, and all the nice features of cohomology, like Poincare duality, are still valid in intersection cohomology. Drawback is this is almost impossible to calculate. Yeah, but it exists. Okay, and this, So the problem is this is incredibly hard to calculate, and there are even cases where one can calculate the intersection cohomology of this moduli space precisely by using this theorem and finding an ad hoc way of calculating this. Yeah, so I've calculated the intersection cohomology of many interesting spaces using this theorem, calculating on this side. Yeah, but well, okay, mathematically this is quite pleasing. This thing now has a structural enhancement as a cohomology theory of some moduli space. Yeah? And this was very nice. This was somehow a theorem which was inspired by physics, by string theory. I had long conversations with Jan Mansrott, and he always explained to me, yes, of course, the Donaldson-Thomas invariance should be related to cohomology of a moduli space. And I always asked him, what moduli space? And he said, yeah, this and that. And I said, no, this moduli space doesn't exist mathematically. Yeah? I have this and that moduli space. Yeah, maybe this is okay. And I said, no, but then cohomology is badly behaved. And it took us years and years to find out we need this moduli space, but we need this cohomology theory, and then mathematically it works. Yeah? So this is what is originally expected by string theory anyway, just cohomology of a Kähler moduli, and this is the mathematical version of it. Yeah, so this is really inspired, heavily inspired by string theory. No, it can be arbitrary thing. Yeah. Yeah, I mean, so if you have something algebraic given by polynomial equations, it can be arbitrary. Yeah. And if you want to do this for topological spaces, you need a certain class of stratified spaces, but that's technical details in Goreski and McPherson works. But if you have something which has an algebraic structure, zeros of polynomial equations, then it's fine anyway. And you can always somehow restore Poincare duality and all these nice things. It's intersection cohomology. Yeah, but you can almost never compute it. Okay. So now finally we are there. Yeah. So now if you go back to the very beginning of my lecture series, I try to motivate everything by this Harvey-Moore work. And they want to define an algebra of BPS state by taking some kind of product, a convolution product along a correspondence, building on the cohomology of moduli spaces. Yeah? And we made this precise, well, not with cohomology of moduli spaces, but with this equivariant cohomology of the parameter space. Yeah? But now we have come full circle and we're finally back to cohomology of moduli spaces. Well, unfortunately, intersection cohomology. Yeah? Okay, so everything is perfect for the symmetric case. And now, finally, in the last about 30 minutes, I have to tell you about the non-symmetric case. And there's one more ingredient which we need: stability. If we have stability chambers, we have wall-crossing behavior. So now I'll write down the wall-crossing formula and then somehow enhance this theorem to the case where you have stability, and then we are done. Yes. All right. Let me just say, as promised by string theory and physics, in some way. Okay. So, part 9. Stability and wall crossing. Why do I use yellow? Okay. No. Final motivating question. What can we do? My God. We do for non-symmetric Q. This is the final section 9, stability and wall crossing. Stability, wall crossing, and Yangians. Lots of buzzwords in this final section. Okay, now finally I should tell you what is the reference for everything I'm doing here. I gave a very, very short introduction to Cohas in the following paper, which is on the archive. And this is the paper which I'm using here as a source all the time, 1904. 1904.09224, together with Hans Franzen on the cohomological Hall algebra of the Kronecker quiver. And this whole lecture series is section 1, generalities on cohomological Hall algebras, which are there summarized on a few pages, which is not really fair. But so this is the basis for this, and for what I'm explaining here. And after this, you can start with reading all the papers of Ben Davison from the last years, and try to strip off all the heavy notation in his papers, but you will somehow recognize all the motives which we discussed here. Yeah. Okay. So, what about symmetric QS? Now we'll do the following. We choose, and this choice is very delicate. You have to make the right choice. Choose a stability function, theta, which a priori is just the linear function on dimension vectors. Yeah? Theta. And from this, you can build a slope stability or a central charge stability. Let me work with slopes because I'm used to it. Define the slope of a quiver representation V. Mu of V as follows. This representation should be non-zero. So V is now short for a collection of vector spaces and a collection of the linear maps. So a full-fledged quiver representation. And I define the slope of it as I take the dimension vector of this V, so just the collection of all the dimension of the vector spaces, and I'm applying this linear function to the dimension, and I'm dividing by the total dimension. So this is dimension not underlined, just total dimension, summing up all the vector dimension of vector spaces. Okay, this is some rational. And this is well defined because I assume the representation V to be non-zero. So this is, using this, I will define slope stability. An equivalent formulation is to work with stability in terms defined in terms of central charge. And just for explaining to you the translation, so equivalently, you can look at the central charge of a quiver representation, Z of V, which is just you take the theta of dimension vector V as the real part of a complex number, and you take its total dimension as the imaginary part. And then you take your usual definition of stability using central charges. Central charge. And I will continue with the slope stability because that's what I'm used to. And now I define the representation to be semi-stable. V is semi-stable. Stable. If the slope drops on subrepresentations. For all 0 not equal to U, proper subrepresentation. Aha. So that is another reason why I explained to you the notion of a subrepresentation in the first lecture. Subrepresentation, if you remember, was you have a subspace in each of the VI, which is compatible with the arrow structure. Yeah? And now we want to put a certain numerical restriction on the whole lattice of subrepresentations. Namely, we want the slope to only decrease or to not increase on subrepresentations. It's a very simple numerical condition. It's in fact a genericity condition. So if there is a semi-stable representation at all, then almost all of them are semi-stable. Yeah? This is a genericity condition. So you're just excluding certain very bad cases. Okay, and so with this we can do several things. We can define, now I'll give you the full definition of moduli spaces of quiver representations in just 2 lines, and I will define a local coha, and then I can formulate the final theorems. So we are almost there. So, space here. So let me now define what is the semi-stable part of the parameter space Rd. Rd, again, is our universal parameter space for all representations of dimension vector D. What is the semi-stable part? This is defined as the set of all these tuples of matrices F alpha, such that the representation on the vector spaces Vi, together with these F alpha, as a representation is semi-stable. That is a certain dense part of the whole RD. So this is sitting in RD densely. I will show you the one key example in a second. And this notion of semi-stability does not depend on the equivalence class of the Quivers representation, because the structure of the set of sub-representations does not change if you stay in the equivalence class. And this means that I can still act with my group GD on this. Yeah? So now I define the moduli space MD SST of Q as the set of closed orbits of the group GD, but not in the whole space, but in this semi-stable part of the space. And this, again, has a structure of an algebraic variety. It's given by polynomial equations but now not in affine space, but in some affine space times a complex times a projective space of some other dimension. Sorry for that. Just explaining this is material for another lecture series. I'm trying to be suggestive. I gave you some details on this moduli space without stability. Yeah, it's given by polynomial equations in affine space. As coordinates, you take traces along cycles. And then I think you can believe me now that we can take closed orbits in this semi-stable locus, and it's given by polynomial equations in affine space cross projective space. There's also a recipe for getting the coordinates in the projective space, but I will not tell you this. I will just show you the one key example where you need this and how it solves all our problems. Okay, so the quiver is, yeah, we're getting closer. This was one of my running examples, but I didn't discuss it yet. That's now time for this quiver. This quiver and the dimension vector is again 1, 1. And the action is the following. ST acts on AB by T by S times A, T by S times B. This is not so far from what we did before with the symmetric quiver, but now the orbit structure is of a totally different nature. Let me draw you a picture of the orbits. Well, there's one orbit, 0. And so you're dilating both coordinates by the same factor. 0 is one orbit. And what are the other orbits? Punctured lines to the origin. Yeah? All lines to the origin. Now, if you ask Hilbert, or if you asked Hilbert in 1900, what is the moduli space? He said, well, okay, sorry, I can only parameterize the closed orbits, so the quotient is a point, because there's only one closed orbit. And they will say, well, too bad, because we're missing many, many orbits. We're missing this whole family of lines to the origin. And by the way, I know a moduli space for lines to the origin. It's called the projective line. Yeah? Lines to the origin in the plane gives the projective line. And Hilbert says, well, sorry, I cannot do that. But then, 60 years later, Mumford said, oh, I have an idea on that. I will just leave away all the bad orbits. That's Mumford's geometric invariant theory. I will just leave away the bad orbits. And what is the recipe for leaving away the bad orbits? Only take semi-stable orbits. So what semi-stable means is that RDSST in this case is C2 without the origin. Okay, now if we are leaving away the origin, if we put a hole in here in the middle, then suddenly all the orbits are closed, and Hilbert says, okay, now I'm back in, I can parameterize these closed orbits, in fact, by the projective line. The moduli space is M the SST of Q is isomorphic to a CP1. Yeah? And that is the essence of this blackboard. But how to do this technically is, of course, a huge story. But everything works mathematically thanks to Hilbert and Mumford. Okay. Yes. Final theorem. So, remember that what I just omitted is you make a choice of this theta. You make a choice of a notion of central charge, and I told you this choice is subtle. And you will see this in the following theorem. So, final theorem, which is combining my own work with Hans Franzen and also, again, Davison and Meinhardt. And our version is for Quivers, and Davison Meinhardt generalizes to Calabi-Yau, three Calabi-Yau categories. Okay, so what you do is, so we need one more assumption, namely, we have again to assume a symmetry. So we have seen this Euler form. If this Euler form is symmetric globally, that was a symmetric quiver. Now we just want to get rid of the symmetric quivers. Now we will only assume this to be symmetric locally. So assume that the restriction of this to the set of the dimension vectors of a fixed slope, dimension vectors over fixed slope, that's a hyperplane in the space of dimension vectors. That's one linear condition. Yeah? And this should be symmetric for all possible slopes. This doesn't look like a natural condition. Yeah? And in particular, it doesn't look like a relaxation of the whole thing being symmetric. Yeah? I mean, so on this one parametric family of hyperplanes, the form has to be symmetric, but not globally. Does this happen? Yes, it happens a lot, actually. There are many, many examples of Quivers where you can choose a theta such that this works. This is a combinatorial thing which I will not discuss, but there are many interesting examples. For example, complete bipartite Quivers. So make this assumption, then define the local coha for a slope S as all the dimension vectors of slope S, and then we are taking the equivariant cohomology, but not of the whole space, but only of the semi-stable part. Local coha for slope S. And before continuing with the theorem, this one's a beast. Yeah? Because this trick, which allowed us to get a shuffle description of the full coha, doesn't work anymore. The trick to get the shuffle description of the full Coha was G dx on RD. RD can be contracted to 0, and then we are done. This doesn't work because 0 is precisely what we omitted and some other bad orbits. So this space is no longer contractible to anything very small. So this cohomology here, this equivariant cohomology, is really, really difficult. And there's no shuffle description of this a priori. Using many of our theorems, there is, again, a shuffle description, but that's a different story. And, okay. So this is very, very difficult in general, but at least if we restrict to dimension vectors over fixed slope, we have confidence that this has a nice structure because there's this symmetry assumption, which was so essential for Efimov. Yeah? So this works, and then indeed you have the following. Now this is huge. Take all these local cohas and take their tensor product. Now, this is a bit scary. This is a tensor product over the rationals. And you have to take an ordered tensor product because there's a natural order on the rationals. And you have to think about this for some time. What does this mean algebraically? How to make sense of infinite order tensor products? A bit non-trivial, has to do with the grading. And these guys are still double graded. It has to do with the grading, and because there is a grading, you can in fact make sense of such products. And from here, you have a map to the full Coha of the quiver Q. This we don't understand because we're in the non-symmetric case. The map from here to here is the following. An element in here is an infinite tensor of elements xs. An ordered infinite tensor of elements xs. This doesn't make sense. So if you think about how to make sense of infinite tensors, what you need is that only finitely many of them are not 1. Yeah, are not. Xs not equal to 1 only for almost always. Aha. So if I have only finitely many in this tensor, I can just take the product. Our theorem is this is an isomorphism, not of algebras, but at least of graded vector spaces. Isomorphic as NQ0 graded vector spaces. Okay, that's the mathematical formulation of the first part of this final theorem. Now I will tell you what this means. When you have a very complicated non-commutative algebra, you want at least to have a normal form for its element, some normal ordering. Yeah? This gives you a normal ordering. Any element in the Coha can be decomposed into a product of elements of the local Cohas in certain ordering, namely ascending slope. Yeah? So this gives a normal ordering. It's not an isomorphism of algebras, but at least it gives some kind of normal form for elements in this algebra. And this is the first step in getting nice structural properties of the Coha. And the second part is then Davis-Meinhardt. Okay, so this is formally equivalent to whatever Walk-Crossing formula you can think of. Yeah? So this is an algebraic upgrade to a Walk-Crossing formula. This is WCF. And final part is that the local Coha itself is not a symmetric algebra like in Efimov's theorem, but you can define a filtration on this, a filtration F. And this filtration is something which mathematically exists, and it comes from deep from the details of intersection cohomologies, the so-called perverse filtration. And so it exists, nobody can ever compute it. But it has a natural filtration, and then you can take the associated gradient with respect to this filtration. Then the algebra becomes simpler, and it is, in fact, then again a symmetric algebra over some primitive part, and this primitive part is again intersection cohomology of moduli spaces. Sum over all D into compactly supported intersection cohomology of these moduli spaces. Okay. So at least I prepared you for this theorem because we did all the individual steps, and now we're just putting everything together. Yeah? We have seen the ingredients in simpler cases. And final thing, and the coh of Q, it feels Yangian. That's not a mathematical statement, but in the few cases where people can compute it, it always looks like not quite a Yangian algebra, but very close to the typical form of relations in a Yangian. This is not yet explored, yeah, but it somehow smells like Yangian spirit. All right, and yeah, this is definitely enough. Thank you very much. Thank you. Yes, please.
Okay, so in the usual story for big divides, you take these modular spaces that typically not compact, you compactify them, they're not a variety anymore, but then you construct critical cycles, integrate, and get numbers.
Yeah.
But here we are working always with non-compact and in cohomology.
Right.
Can you say a bit more of the two are related?
No, I would love to be able to. Yeah. Okay. So so here's the story for this. This is in general still this moduli space is given by polynomial equations in affine cross-projective space. If your quiver has no oriented cycles, there's no affine part. You're just closed in projective space. So at least you have something compact, but still singular. Yeah? And the singularities come from properly semi-stable representations. Okay. But there's a large part which is non-singular. This is this moduli space of stables. And this is a singular compactification of it. If only we had a non-singular compactification, if we had a smooth compactification of this non-compact moduli space, then we could get rid of all the intersection homology. Then we could just replace it by ordinary cohomology. But nobody knows how to mathematically construct such smooth compactifications. Just in extremely small cases, like the dimension vector is 2. Yeah? Then we can do it. But in general, nobody knows how to do this mathematically. That's the problem. And this is what we really hope, and this is somehow also predicted from the physics, that you have such a smooth compactification, but mathematically, I don't see it anywhere.
So the technical assumption of no closed loop is just so it automatically compact, even though
Yes, exactly. Yeah. Because we have seen this. If your quiver is acyclic, then in the full space you have no closed orbits, and then actually you don't have this affine part. Yeah. Because this affine part always comes from oriented cycles. Yes, please.
If we change theta, how do things change?
Yeah, dramatically. I mean, look at this isomorphism there. The right-hand side is just the coa of Q. There's no slope involved. On the left-hand side, there's a stability involved. Yeah. So that means you can say you take a theta and a theta prime, and for both of them, you have such a tensor product decomposition on the left-hand side, and it's the isomorphic because it's the same thing, the full coha, and that is wall crossing. I will show you the simplest example. I mean, in general, it just changes drastically. Let me give you the example of the quiver, which is just a single arrow, the easiest non-symmetric case. Yeah? In this case, you can take a trivial stability, and I've shown you these generators psi and eta yesterday. Yeah? And so the coha of this is, on the one hand side, isomorphic to an infinite exterior algebra in all the psi's, tensor infinite exterior algebra in the etas. That's for the trivial stability. And for the non-trivial stability, there's only one. For the non-trivial stability, you see that you get a different normal ordering. Namely, it starts with the etas, then you need something new, and then finally the psi's. And you have a third part appearing in the middle. So this tells you you have two different normal orderings for the elements in the Coha. You can write it as a product of, well, first the psi and then the eta generators, or you can write it as an ordered product, first the eta generators, then some new generators, which are not unique, you have to make a choice, and then the psi generators. And that is the simplest example of word crossing. And by the way, just 1 second. So you have two terms on the left and three terms on the right. If you now look at these motivic generating series, these partition functions, what you get is the 5-term identity for the quantum dilogarithm. You have two terms on the left and a threefold product on the right. Yeah? So this is an algebraic version of dilogarithm identities. Your question. It's not explicit. If you work out these Z, these partition functions, it's precisely the quantum dilogarithm identity.
Oh, yes. So that's also part of the theorem? Oh, I see.
Yeah. You can make this theorem much longer if you write down all the implications. But that's somehow an algebraic enhancement of Q dialog identities. Yeah. And if you take this full theorem that the Coha is this infinite product, then you get, in general, infinite products of quantum dilogarithms. And this you can look up in a recent paper of mine from last year, which is just called wild quantum dilogarithm identities. Because they're really wild, they're really properly infinite. And yeah. So there I just take this theorem and write down what happens on the level of the partition function, and then you get all sorts of crazy dialog. No. Yeah. No, it works. Yeah, it works. Yeah. Okay. So, for example, yeah. How does it work? So then, instead of making sense of an infinite tensor product, we have to make sense of an infinite ordered product of formal power series. And so you can see this as follows. So say you're working in Q, X, Y, in a formal power series ring in two variables. You can make sense of a product of a series Fs of X, Y, where S runs over the rationals, and this is an ordered product. Now we don't need the ordering because this is commutative. Is well defined if any of these series Fs of xy is a series starting with constant term 1, and it is a series containing only terms x to the a, y to the b, where the slope, which is irrational, is written as a by b. Yeah? So this is the x power, this is the y power, and you are assuming that all the individual Fs only live on a certain ray. Think of scattering diagrams. It's all living on a certain ray, yeah? And then you can well define an ordered product over the rays with increasing slope or decreasing slope. And the constant term of the series has to be 1, yeah? And then this is well defined. And if you upgrade this algebraically, then you can well define these infinite tensor products. Yeah. Yeah. That's in here. If you have an algebra which is filtered and the associated gradient is a symmetric algebra, this means PBW. Yeah, okay. So yeah, in terms of this normal ordering, you can do the following. Choose generators of all these cohomology groups. Absolutely impossible to calculate, but let's assume we have made a choice. Then take monomials in these generators. Then by Poincare-Birkhoff-Witt, we have a basis of the local coha. And now you take these bases of the local coha and you glue them all together in a certain ordering. Yeah, this is this normal ordering part. And then you have a basis for the whole coha. No, no. I mean, there are no relations there. This is really an isomorphism. In this tensor product, you have no relations. And here, the only relations are of quadratic nature. This is Poincare-Birkhoff-Witt, yeah? And we don't know the precise quadratic nature. We only know they feel like Yangian relations, yeah? But there's only quadratic relations. But if you just, I mean, whatever these quadratic relations are, just take ordered monomials in the generators here, and then take ordered monomials in the whole thing, and then you have a basis for the full coha. Yeah, that's what it gives you. And for example, you can really work this out in this particular example of this two parallel arrows. There you can really write this down. This is also in this paper for which I've given you a reference. There we worked out this whole normal ordering thing. That's before taking the associated. I mean, after associated gradient, it's really just a graded symmetric algebra, just commutator or anti-commutator equals 0. And before taking the grading, it's commutator or anti-commutator is some quadratic expression. And this looks like Yangian in all known cases. Yeah. Thank you very much for your attention.